muting you to manage any ambient noise. It's really good to see you all this evening. We'll just wait about 2 more minutes until 6:35 to go ahead and get started, but I'm happy to see all your faces and really happy to have you here this evening. Thank you. Thank you all for being here this evening. We're so happy to have you. I know many of you. I'm Krista Hoffman-Longton. I'm an assistant dean in the IU Medical School and an assistant professor in communication studies at IUPUI. And as usual, on the last Tuesday of the month, I'm really happy to welcome all of you to Books, Booze, and Brains. We're really happy to have you here tonight, in part because we have some exciting announcements and we have a great expert guest, and I'm really excited to talk about astrophysics tonight. So with that in mind, I'm going to share my screen so that we can go ahead and get started. And while I do that, I'll just share with you, as usual, a little reminder of the ground rules for an evening like this. And the first one, of course, is we want to encourage you to make sure that you're muted when you're not talking. Just helps us, again, to manage the ambient noise. Please be yourself and be respectful of others. Sometimes in this online space, we can forget that there's a real person on the other end, and we always want to make sure that we're kind to one another. Ask questions using the chat feature, which is on your toolbar, usually at the bottom of your screen. And please think before you type that question. You can use your reactions feature on the toolbar. Those are like emojis. So if Dr. Gavrin or if I say something or one of the participants maybe responds and you want to co-sign that, use that thumbs up button. That's a great way to do that. Megan from Indiana Humanities is going to monitor the chat for us. Andy and I will get to talking, and we get excited about these topics, and sometimes we might miss a question. That's not about you, that's just about us having a great conversation. So Megan will be sure to keep us honest and make sure we get all of your questions answered tonight. And then lastly, after the turn and talk conversations, if you want to turn on your mic to speak, we're happy to have you do that. There is a half-second delay. So when you kind of click your button, then take a breath and then speak your answer, and we'll make sure to get all of your responses there. It's always great to see all of you. I am here to welcome you again to Books, Booze, and Brains. We have a few sponsors that we always like to thank: Indiana Humanities, Indiana Sciences and March for Science, the Indianapolis Public Library, and Central Indiana Science Outreach. And we have folks from each of those great organizations here in the room with us. Before we get started with our program for tonight, I have just a few updates that are important, I think, for those of you that are regulars to the program. So for starters, we want to let you know that we really appreciate those of you who filled out our survey. If for some reason you didn't get a chance to fill out the survey, no worries there, because I have to say it was about the middle of the road group of answers that we could possibly get. So the bell curve was strong with all of you. And what we asked was whether you were ready to come back in person. And so we, like I said, we're very middle of the road, it seemed, as a group. And so we try to strike a balance with our fall lineup. So as you know, we take the month of June off, and we come back in July and take us through November. So in July, we'll be back on Zoom via a regular Zoom, and then also our usual live stream. In August and September, and I'll talk about those in a minute, we will do our best to be in person, likely outdoors, pending any audio and public health restrictions. As some of you know, if you've done any audio work, miking a group of people outdoors is much harder than miking a group of people indoors. So we will do our best to find a venue that helps everyone to feel comfortable and to support the program. And then in October and November, we're going to be back on Zoom, and that's by design, and I'll talk about why in just a minute. So next slide here. Here is our lineup. This is very exciting, I think, for the, and I'm going to make that a little bigger so y'all can see it. for the fall. So in July, we are reading Buzz, Sting, Bite, Why We Need Insects. I think very apropos for July, and also given our experience with cicadas that is to be coming, or for some of you might be here. In August, we are reading a great book about mushrooms, called Entangled Life. I'm really excited about this one. As we've done in years past, we try to at least choose one fiction book. So we are reading Octavia Butler's collection of short stories called Blood Child and Other Short Stories. And then, super exciting, in the month of October, Stephanie Strategy is going to be here with us. She wrote a book called The Perfect Predator, A Scientist's Race to Save Her Husband from a Deadly Superbug. And so one of the reasons why we'll be on Zoom in October is that Stephanie is going to be our guest expert and also the author that month. So that's really exciting. And then for November, we're reading Misbehaving, the Making of Behavioral Economics. We haven't done an economics book, and so we're really excited about that as well. So as usual, we will stay the last Tuesday of the month from 6:30 to 8. We're so happy to have all of you, and we think that this is going to be a really exciting season. So as usual, the easiest way to get information about these events is to just connect with us on Facebook. So if you just if you just search in the Facebook tool, Books, Booze, and Brains, you'll find our events. Those events are updated with the Zoom link as you need them, and also updated with any additional information. You should also be on our mailing list, but if you're not on our mailing list, you can private chat Megan from Indiana Humanities, and she will add you to the mailing list. So thank you all for doing that. Last item of kind of update, and that is that I feel a little dissonance about this, but I am reporting, I guess, that I am going to step away as the facilitator of Books, Booze, and Brains. I have so loved spending the last few years with each and every one of you and getting to know you and learning more about all of these great science topics with all of you. And now is a good time for a transition. I'll also share that I'm teaching on Wednesday nights in the fall, so that makes it really hard, but I'm going to try to make it as a participant and bring a few students every now and then. That said, we are looking for a new facilitator, and I put a call out to a number of my colleagues, but I also want to make sure that I open it up to folks that are not in my immediate network, as well as the immediate network of the planning committee. So if you are interested in being a facilitator, want to learn more about it, you're welcome to reach out to me. We have a little process, you would say, for letting us know that you're interested in serving as the facilitator. And we gave you a little deadline in June because we will try to transition in the next season. I will share with you that I'm not going very far. I'm still going to be here. I'm still going to attend as I can, but so I'll be there to support whomever decides to be the facilitator. But I just want to say, and I'll again echo this at the end, but the amazing group of individuals who help make this possible every month, including the folks from Indiana Humanities, the Indianapolis Public Library, Central Indiana Science Outreach, and Indiana Sciences. It has been such a pleasure to get an opportunity to work with all of you. Thank you all so much for your hard work. And that ends my public service announcement for the night. Let's get to Books, Booze, and Brains, all right? Okay. So, as usual, would love to see your faces. If you're welcome, or if you are interested in turning your camera on, you're welcome. If not, that's okay too. We are always happy to welcome children and four-legged coworkers and friends if they show up in your screen. Andy, we are going to get started talking about this, and I'm wondering if we can begin by asking you to introduce yourself, and we'll give you a warm Books, Booze, and Brains welcome, and tell us a little bit about yourself and how your work relates to this book. You got to unmute yourself though first.
There we go. All right, can you hear me now? All right. So I've been a faculty member in the physics department at IUPUI since 1995. Moved here from Maryland, where I had been at the National Institute for Standards and Technology for a few years. I've been chair of the physics department for 12 years and I'm just stepping down June 30th. So I will be returning to the role of regular faculty member at that time. I've always loved astrophysics. I want to tell you right now, though, I'm not an astrophysicist. My physics research has been initially for a very long time in magnetic materials and materials physics generally. And more recently, I've been doing a lot of work with physics education research, which is sort of a brand new field studying how people learn physics and what we can do to make that better. But I still love getting out with my telescope, reading about astrophysics, both in the news and sometimes in the research literature when I get the chance. And I'm just looking forward to sharing my excitement with these topics with you and connecting this book to other ideas. I'm always up for a good conversation, and we'll see where this goes.
Thanks, Andy. We're so happy to have you. So I want to follow up on something that you said there, in part because it's interesting to me, and I get to do that because I'm a facilitator. So all right, this is my last moment. You mentioned your recent research in physics education. Why do you think it is? I mean, this book is really designed for a very broad audience. So why is it that physics education is a relatively young field, particularly given, that Neil deGrasse Tyson, and I don't know if there are other sort of popular press physicists, I guess Brian Greene comes to mind, right, who have been doing this work around helping folks understand that you can see physics in the world every day, that it's not just something that happens sort of theoretically. Do you want to talk more about that?
Sure. So physics, I mean, Neil deGrasse Tyson is one of the greats at the moment of popularizing physics and bringing physics to the broad audience. And it's really an essential role. It goes back a long way. I mean, certainly you mentioned Brian Greene, but those of us who have a few gray hairs on our heads certainly remember Carl Sagan. And there have been others before them. And actually, if you look back deeper into the history, it was a lot more common for scientists to address the public. Back in the old country, as it were, back when the Royal Society was young, the idea of explaining science to at least to the well-heeled, perhaps not to everybody, but it was always out there. Scientists have always wanted to bring the excitement of what we do to the public. Now, I do want to make a distinction, though, between doing that, explaining science, and studying how science is learned, which is really more what you think of as a typical research kind of thing. It's that really deep dive where we're going to go in and try and understand what it is exactly about a particular topic that's hard for students to understand. People do things like a lot of the tools of cognitive psychology are now being adopted by scientists, not only physicists, but chemists and mathematicians and others, to do things like understand when a student looks at a problem, where do they look? And there are so-called eye tracker systems that as a student pulls something up on a computer screen that then watches their eyes and checks to see, are they looking at the figure first? Are they reading the text? Are they going back and forth? What are they doing to make sense of what they're being shown? So, the physics research, the physics education research has a host of things like that. My particular interest has been in how we use technology in the classroom and also how we use technology outside the classroom to hold students' attention, to keep them engaged, to keep them focused on the important topics.
I think, when we think about a book like this, and I think about the idea that, actually, Andy, I don't know this, maybe you can say more about this. It's my understanding, and again, physics is not my area of research, but it's my understanding that there has been movement, at least as far as I know, in the life sciences. I don't know as much about the physical sciences, and sort of creating sections of courses for, let's say, majors versus non-majors, right? Folks that are going to kind of grow up to become chemists and physicists and biologists, et cetera. And then folks that maybe are choosing other fields. How does that relate to studying how, like, do folks who are pursuing the field think differently than others? You may not know the answer to that question. I'm just kind of thinking about how we frame these scientific concepts for both folks who are pursuing expertise and folks that are maybe pursuing popular understanding. And maybe it's the same thing.
Yeah, no, that's a fascinating question, actually. And I'm not even sure that there's complete agreement on those questions or how to approach those things, either in physics or in the life sciences or other areas. You know, teaching is a fantastic avocation, and you know, I love physics and I love teaching it, and both are interesting in their own rights. And I am looking at the list of people here, and I see some other people that I know are great teachers in other subjects as well. I want to make just a quick shout out to Marianne Wokak, who's been a friend and colleague for many, many years, and a great teacher. So within this, so in physics, there's always been, for many, many years, I mean, when I was in college, there were separate sections for students, in fact, separate courses for physics majors than there were for students who simply needed physics to satisfy a requirement for an engineering or chemistry or other degree. Although there was always a lot of crosstalk between them. And how those differ could be different in different fields. You know, the same thing was true in calculus. There was a calculus for math majors and there was calculus for everybody else. And I guess there are different philosophies about what should be different between those two. To me, it's not the topics that are the most important. The most important thing actually is that question of how do we think? So in all those subjects, all those courses, including the ones that aren't for majors, how do we think about these topics is the most important thing. And the number of details that get covered is the least important. So the course for physics majors isn't the one that covers the most. It might be the one that goes into the greatest depth, or covers a few extra topics, or uses a different formalism, or assumes more background. But how we think should be the same for all of them, in my view.
So I think that's a really good point. And I will say, as a, teacher of communication, as a scholar of science communication, I feel very much the same, that I often think that it's not about necessarily the parts and pieces of the content as much as it is about thinking about the process and teaching about how to think about the process. So that leads me to our first turn and talk question of the evening, and it's actually the beginning of the book. So, all of you know that I love to start many of our conversations with one of these, a quote from the book, in part because it's provocative, and even if you've not read the book, I think that the quotes are usually interesting. So the quote that I want to start with is, I'm going to go ahead and put it in the chat, is at the beginning of the book, right? And he starts the book, Neil deGrasse Tyson starts the book by saying, the universe is under no obligation to make sense to you. And so my question for all of you to answer in your breakout rooms or to talk with one another about is, what is it about physics, specifically astrophysics, that makes it hard for some folks that are not in the field? And again, I don't want to make any assumptions, but I do know that part of the reason Neil deGrasse Tyson says he wrote this book is that physics gets a little bit of a bad rap, particularly astrophysics, of being hard to understand. So what is it about this field in particular that you think makes it hard for folks broadly to understand? So you've got that chat. I'm going to go ahead and get breakout rooms set up. As a reminder, you'll be headed into a breakout room with, I hope, about 4 or so participants. Andy, just so that you know, you'll get invited to a breakout room as well. Please just stay here with me in the main room. Okay. You and I will answer this question in the main room while our participants are in the breakout room, solving all the world's problems. Okay. So hang out here with me in the main room. Again, you won't have a facilitator. You'll be self-facilitated in your breakout rooms. So just take, I'm going to say, about 7 or 8 minutes to answer this question, which is in response to that first quote of the book. What is it about physics, specifically astrophysics, that might make it hard for folks to make sense of? So let me go ahead and get those rooms open. And as I mentioned, Andy, you can go ahead and stay in the main room if you would.
Sure.
Thanks. And for folks who are in the main room here, you're welcome to stay in the main room. We'll just go ahead and have a conversation. So Jeff, it looks like, is our only participant who chose to stay in the main room. Feel free to hang out. Andy and I are just going to chat while we'll monitor the time in the breakout rooms. So Andy, I mean, I imagine, I would guess, I don't know, maybe this is not true. Did physics conceptually come easily to you as a student?
No, I wouldn't say so. I mean, some parts of it did, some parts of it didn't, but I don't think I have any special inborn ability to understand.
That was sort of my question, I think.
Yeah, no, understanding, nobody's born knowing how to do physics. It comes from work, like understanding anything else. I mean, I can't play video games worth a darn. I never could. And I grew up in that era where, that was the thing to do. When you went out with friends, you went to a bar and you played one of those games. There were arcades everywhere. And other people could learn to use a joystick. And I never put in the time. But I put in the time on physics. And so that each little bit that you learn makes it easier to learn the next bit. And I think that's true of any subject.
I agree with you. I mean, I think,
Tyson is correct, of course, in that statement, but I would like to add that human biology is also under no obligation to be understandable to you, and neither is the US economy or medieval literature.
Right.
In fact, the universe is under, none of those things are under any obligations at all to any of us.
And yet that doesn't stop us from trying to know and understand them.
Yeah. So,
any of those things.
Right. If we put in some time, we'll get some benefit out. And the more time we put in, the more we'll probably get.
And I think to some extent that, part of what, so I guess I'll ask you, because I think you probably at least know and understand Tyson's perspective more than I do. Why make such a provocative statement at the beginning of a book like this? What is he trying to invoke in the reader?
Well, actually, I think that's your field, not mine. I mean, that's a communication.
I have some ideas.
I think he's trying to get people a bit agitated. I think he's trying to get their attention. This guy is making a living as a science communicator, and he knows that it's important to get a hook into people and get their attention, because people's attention is a rare commodity these days.
Absolutely.
And if you lose people, you don't have a second chance.
I think it's, to me anyway, I'm not sure that this is entirely my field, though I do appreciate the sort of storytelling that comes into, starting with a quote like this. For me, the reason why that question is provocative is that there's a little bit of an, oh yeah, like, I'm going to show it how to make sense to me kind of thing, which I actually think is genius on, Tyson's part. But I think that the other piece of it is that I think it helps you to understand the scope at which physics exists in the world to non-physicists as invisible.
Mhm.
That for many people who don't study physics, who don't think about physics on a regular basis, physics as a concept, astrophysics specifically, is relatively invisible. It's something that we often, he spends a lot of time talking about the idea that many of the things that we know, particularly from the last 100 years of study in physics, are things that don't necessarily fit well within our understood five senses.
Yeah, I mean, that's certainly true. Although astrophysics, it gets much better press than, say, nuclear physics or plasma physics.
Oh, that's interesting. I didn't know that. Can you say more about that?
Well, I mean, if you open up the newspaper, open up the New York Times website or the Indianapolis Star or any newspaper, and just start looking for science articles. The most common ones will be medicine and other things that sort of, there's a feeling that people have, can make some practical use of.
Always the applied. I agree.
Nutrition, things like that.
Sure.
But if you now say, all right, I'm going to focus on physics and chemistry, let's say, you're going to see more about astrophysics than almost anything else. I mean, you're never going to see anything about plasma physics, or almost never. Whereas, there's all kinds of articles out there. Tonight, I have the moon in my background. Technically, the full moon is tomorrow, but really there's an eclipse of the moon, which happens on some full moons. It won't be visible in Indianapolis. We're just a little too far east, but people on the West Coast will be able to see it. It will be late at night for them, whereas for us, the sun will be coming up just as the eclipse begins, so the moon will be setting. That kind of thing shows up in the newspaper. When was the last time you saw something about, I don't know, crystallography showing up in the newspaper? It never happens. People they like, the Hubble Space Telescope produces all these cool images, and things are big and exciting, and there's often good pictures, and people like those things. They make good stories.
Right. And when I think about, again, kind of what, to your point, what plays well in the news, right? It is, and that's, I think, to some extent, what Tyson is sort of saying in his comment here is that there are parts of physics that are not sexy, but are important. And that, that it, even though it doesn't make sense to you, that doesn't mean that it isn't important. And I think that he does a really good job of trying to create a sense of wonder and a sense of reverence, maybe, for, for understanding these concepts within the context of day-to-day living outside of science.
Right. And the things that happen in astrophysics, I mean, the part of physics that people see is things like, if you throw something, what kind of trajectory it takes. I did an interview right before the Sweet 16 this year about the physics of free throws, which is a phrase that I have great difficulty saying.
That is a hard phrase, the physics of free throws. Yeah. No, I don't think I can do that. Good on ya.
Say like 50 times in 3 minutes, and I goofed it up over and over again.
Is it easier to say pre-throw physics?
Maybe.
I'm not sure.
Probably not, no.
We need another colleague.
Not based on what you just said. But things like if you want to understand what happens inside stars, it's very hard because you just never, ever get to see nuclear fusion happening in your
Right.
daily life. There is no place that we can point to and say, well, it's just like this thing that happens in your kitchen, or it's just like this thing that happens in your garage. There's just nothing like that. So when you go to understand what's happening in the core of the star, it's just harder. You've got less to hang your hat on.
That's a great point. I think especially for me as, somebody who's like thinks about science communication, thinks about how we teach communication, is sort of talking about the idea that for some of these concepts, and I think, again, Tyson does as good a job as you can to build metaphors and other sort of analogous strategies to be able to connect, concepts that you can't see with or I will say that you can't perceive with your five senses, to make sense of them for the audience. But to some extent, and I think he does a good job, this is easy for me to say, anthropomorphizes, I think I said that right, a number of the concepts as a tool to help us make sense of them. And I think that, again, as we think about what it means to make sense and why we would want to make sense in the first place, I think it's worth sort of unpacking what tools are available to us and to what end.
Absolutely.
So folks are back in the main room here, and I'm going to remove our kind of pins here so that we can, if you'd like, you can look at everyone in gallery view at the top right-hand corner of your screen. And one of the things we always love to do at Books, Booze, and Brains is kind of hear from everyone, hear how your breakout conversations went. It's really a hallmark of that public conversation that we love to have. And maybe your group generated a question for Andy, which is fine as well. And if that's the case, go ahead and put that in the chat. But if we have one or two participants, I would love to hear a little bit from maybe one or two of the groups about the conversation that you had, or about what questions you generated as you had your conversation in your small groups. So I'll go ahead and pause here for a second in my talking and leave the floor open. Would anyone in the room like to share how your conversation went, or if a question was generated for Andy from your small group? And you're welcome to raise your hand. Looks like Hannah's raising her hand. Hannah, go ahead if you would like to unmute yourself and say hello to Dr. Gavrin.
Hi, Dr. Gavrin. I just wanted to mention our group is kind of in consensus that learning about astrophysics, and especially astrophysics, it's harder to visualize in addition to not being something we see in our everyday lives. So like you can learn about the human body and microorganisms or geology, and some of that stuff's not what you can actually see, but at least it's easier to visualize. And astrophysics, you get into really weird kind of illogical feeling things. Someone in our group also brought up the fact that you kind of have to turn on a different part of your brain almost when you're learning these things, which may also be why it feels a little less accessible to some.
I'm sorry, did you say turn on or turn off part of
Turn on, sorry. Turn on a different portion of the brain.
What do you think, Andy? Is that true in your experience with students? Do your students sort of turn on or turn off a different part of your brain, or their brain?
I'm not sure. I think that, and I said earlier, I'm really a condensed matter physicist, not an astrophysicist. But even worse, I'm most certainly not a cognitive psychologist. However, I'm just going to go out on a limb and say that a big part of learning is making connections between the new thing you're trying to learn and the old stuff that you already know. So we learn by sort of connecting, creating new webs of ideas and saying, all right, this is like this is like that. This shares some commonalities with this other thing that I know. And that's really what we're doing when we use that phrase, making sense. We're making connections between the new stuff and the stuff that we feel already makes sense to us. So yeah, we do that by making analogies and metaphors, and really good science communicators like Tyson are great at creating those metaphors. But we also always know there's a certain risk with a metaphor, which is that you can torture it. You can go overboard with a metaphor and it's now telling you something that isn't really true anymore. So there's always a little push and pull, a little give and take between the metaphor as explanation and the actual thing. And I suspect that anyone that's ever taught anything to anybody has gone through that experience of saying, oh, well, it's kind of like this. And then the person says, yeah, so does that mean, are you saying this? And you say, yeah, that's right. And they say, well, does that also mean this? And you're like, oh, no, wait a minute now, you're taking it too far.
I think that's a great point, Andy. I will share with all of you that I have a really great colleague in communication studies at IUPUI, Beth Gehring, who studies metaphor and studies sort of how metaphor is used, and particularly in the context of health and illness. And I think that that's another space where we see metaphor potentially being helpful. But to your point, Andy, like belaboring it doesn't serve us well. And I think that the idea of making sense of or making meaning of is a really important part of a book like this one, right? Because it does sort of help us to understand something in the context of our lives, particularly something that we can't, as Jay mentioned in the chat, we can't necessarily perceive with our senses. And that's something that Tyson really, that he really explores in this book. And then I think many of you know that when I prep for an evening like tonight, I always go to watch or listen to a couple of podcasts or videos of the author speaking. And that's one of the things that he spends a lot of time talking about, the idea that we have a set of senses, right? Most folks say 5, but there are technically more than that. And that we use those senses as a tool to interpret the world. And one of the reasons why this subject in particular might potentially be hard is that it's harder for us to use those traditional 5 senses to truly, like in air quotes, make sense of these concepts that to some extent seem nonsensical.
Mm-hmm.
So I want to talk about a quote, Andy, for you specifically that came that to me as I read, this was a quote that I think it's a pretty bold quote. And I'm wondering if you can talk to me a little bit about your field and a little bit more about why an author like Tyson, who I know is, I'm aware that Tyson spends most of his time doing public engagement work now, despite his training. So for those of you that read the book, this is on page 35 of my edition. And I'm sure Andy searched for the word universality. So page 35, the universality of physical laws drives science discovery like nothing else. I felt like that was pretty bold. I mean, I'm not a physicist, but I have some more to say in my field that this concept drives discovery, like nothing else. That's pretty provocative. Can you talk a little bit about what Tyson means when he says the universality of physical laws and why he might make a claim like that?
Yeah, I think this is a great question, and in large part because it touches on what we were just talking about, which is making those connections between things that we can touch and things that we can't. What does he even mean by that? The universality of physical laws. Let me just give a critical example from Isaac Newton. That there's that law that gets taught in high school physics classes that the gravitational force between 2 objects is this constant G times the 2 masses, the mass of each object, and divided by the square of the distance. And we call that Newton's law of universal gravitation. And this is part of the genius of Isaac Newton. What he did there was what is important, most important, isn't that there's this constant G or that it's the product of the masses or even the inverse square part, though that happens to be very important. The genius was in saying that the laws that cause things like apples to fall to the ground are the same laws that cause the planets to go around the sun. He was really saying the law is universal. He's saying the things that we can touch and mess around with here with springs and strings are the same as the things that guide the planets in their orbits. He's connecting what's happening on the ground to what happens in the heavens. And, at a time when the heavens were truly the realm of God and not of man, there was no a priori reason to believe that. But he could say, all right, I'm going to do experiments and understand how gravity works on Earth, and then use mathematics to check to see whether that same law explains the motion of the planets. Find that in fact it does, and write it all up as a complete package. I understand gravity. I understand the motion of the planets around the sun. I understand the motion of the moon around the Earth. And it's all based on the same single idea. That's a really powerful discovery.
It's super, just hearing you talk about it that way, sort of change, like I think about Newton doing his thing, and the idea that it would completely change the way that you think about proving your thinking to some extent, right? And so can you talk about the relationship between certain sort of Newton's work around this and using mathematics as a tool to be able to understand the physical world?
Sure, absolutely. So this is what we do in physics. And I'm going to kind of have to weave in and out of your question a little bit. So to have an idea, a theory, is more than just to have sort of a vague idea. Oh, I think this happens because it happens. The Earth, things fall because the Earth attracts things. Well, that's not saying anything. There's no testable part of that. But once you get into mathematical expression of how that attraction works, how does it depend on other quantities, that you can then start doing experiments and testing. That's sort of the gold standard in physics, is to be able to make predictions of things that you haven't tried yet, that are borne out by the ideas that you put in. There's other pieces of it. Can you repeat the question? I want to, because there was nuance there, and I want to make sure I capture several.
In theory, I can repeat the question. That's ironic. I think the question was essentially about sort of I'm thinking about Newton at the time being able to use mathematics as a tool to be able to better explain and understand the physical world, and how that changed the way we thought about understanding the physical world, right? So he was sort of using math in a way that, as I understand, and again, not a scientist, but as I understand, really hadn't been used up until then.
Okay, so Newton certainly was a brilliant mathematician. I as a physicist, I'll claim the guy and say, oh yeah, he's one of the great physicists of all time. But I think any mathematician would also say, hey, hang on a minute. He's one of the great mathematicians of all time. And he certainly did develop large chunks, the whole idea of calculus and how we deal with quantities that vary continuously as opposed to numbers and fractions. He did a ton of that, and he was a huge contributor. As far as the idea of using mathematics to model things in nature, I think it predates him a little bit. And I would probably shout out to Galileo as someone that really started doing that. Galileo famously did this experiment. The stories vary, but some people say he was bored in church and he was watching the chandeliers swing and using his own pulse as a timepiece to measure the swings of the chandeliers in the cathedral. And developing a mathematical understanding of how the period of a pendulum varies with the length of the cord that it's hanging from, essentially. So there were others who started that idea, but I think it was an idea that was unique to physics for a very long time. More recently, chemistry, biology, all of the other sciences have adopted mathematical modeling to one extent or another. But this idea that we can take mathematics and build a model of nature in that true sense, where I'm going to step back and answer my own question. What's a model? A model is a version of something that leaves out some of the details. You know, a plastic model car is like a car, but it's smaller than a car, and different model cars will have different features.
I often think about that as my colleagues in the med school often talk about mouse models.
Yes.
Right? Like that's another place where we use the term model that is, as you said, sort of parts are left out, right?
The mouse is a model of other organisms because it's one that's easy to work with. You can have many of them around. They're comparatively inexpensive to feed, although I know colleagues who keep mice are never happy with how much, in fact, they cost. But in physics and in other fields now, we build models out of mathematics. And then we can manipulate those models according to the rules of mathematics and say, all right, what if we made this thing twice as big? Or we wait for a very long time? Or we make this part half the size of that other part? Or we look at the ratio, how does this thing vary when we vary the ratio between these two quantities? And then by doing the math, we can make predictions about how the real thing would behave if we made those changes. And those then become testable hypotheses. Those become experiments that we can do. Now, in astrophysics, it's challenging because you can't just build, say, 100 stars and keep 50 of them as your control group and then do something to the other 50 and see what happens. So astrophysicists are limited in a peculiar way that, for instance, biologists and chemists often are not. In the life sciences, ecology is like that. You can't just set up 50 rainforests and see how they develop under different conditions. In earth science, you can't just set up 50 different volcanoes and try them with a different range of sizes. So, this whole idea of making a control sample and whatnot, that's science the way we teach in middle school, but it's not actually a technique that's available to every scientist.
But I think that your question here actually, or just the comments that you've made really get us to the next turn and talk question, which is about the humanness of studying science, which is one of my favorite things to talk about, as you know. So our next turn and talk question comes a little bit later in the book, but I think relates a lot to what Andy was saying just now. And one of the things that I think runs through this book is Tyson does a wonderful job of helping us to think about how humans misperceive science on the regular, how humans just really don't do a good job of understanding their perception in the context of others. I'll share with everyone, as Andy and I were getting ready for tonight, we talked about the idea of how humans misperceive risk, right? In the context of the pandemic, we know that we're terrible at perceiving risk. We know the science of it, and yet still our emotions get in the way. So the quote that is our next sort of jumping off point comes from page 171 of my edition of the book. And I'm going to go ahead and put it in the chat for all of you. So on page 151, excuse me. Tyson talks about how slowly the telescope developed, particularly to see bands of light invisible to the human eye. And he actually blames human hubris for this lack of speed of development, right? He sort of argues that the reason why the telescope didn't develop as quickly as maybe it should have or could have is that we as humans sort of got in the way of saying, well, this can't possibly be true because we can't see it with our eyes. And so I'm wondering if you all in your groups can think about what other scientific discoveries may have been hindered or may continue to be hindered by human hubris. And why do you think that is the case? So what is it about our humanness that might potentially get in the way of scientific discovery? And so with that, I'll go ahead and open the breakout rooms. And I mentioned this earlier, but Michael had a great question that we'll be sure to answer on the way back. And Joseph and Joan, thank you for that comment. I think that that's a great example of the place where that term model is used. So I'm going to open the breakout rooms here. I'll give you about 7 minutes or so in your breakout rooms, and then I'll call you back. And again, Andy, you're going to stay here with me in the main room. Thanks. Just monitoring. It looks like everybody's headed into their breakout rooms who might be there.
For some reason, I didn't get an invite, Krista.
Would you? That's okay. I'm going to go ahead and send you to room 2 if that's cool, Megan. There you go. Let me know if that doesn't show up for you. All right. So here we are again, Andy, in the main room with the live stream audience.
Okay.
So I heard like the concept of hubris is always fun for me to talk about in science because I think it is sort of I mean it's probably in part one of the things that sense of wonder, the sense of hubris, right? Things that these are quintessentially human. So why do you think it is that that the telescope develops so slowly? Is it hubris, do you think, as Tyson sort of posits?
I don't know. You know, I was thinking about this as soon as you said it, because I'm not sure the telescope developed that slowly. There were certainly technological hurdles.
Sure.
There were also reasons to believe that it wouldn't be as productive. I mean, for instance, so the types of telescopes that we have. So there's telescopes that we use to study visible light, and that's the thing that he said. Okay, you know, that came first, and then we didn't look into the ultraviolet or X-rays or infrared or other things for so long. Well, first of all, the atmosphere is opaque to a lot of those things.
Right.
We can see a little bit of ultraviolet through the atmosphere, but basically the sun is about the only thing bright enough. All other ultraviolet astronomy is done from orbit, or at least from high altitude balloons. Infrared is not much better. And the same goes with X-rays and gamma rays. And there, you know, we didn't even know those things existed for much longer. And X-rays were only discovered at the beginning of the 20th century. And for a very long time, we didn't know how to image them. We could detect them, but we couldn't say they were coming from this direction or that direction. So technologically, it's pretty hard. Now, it may well be that it could have happened 20, 30, 40 years earlier, but not 200 years earlier. Radio is the one thing that really could have happened significantly earlier.
Oh, I'm so excited about this. Okay, this is exciting. I will say that this time last year, was for the first time reading. If you've not read it yet, I would highly recommend All the Light We Cannot See. Do you know this book, this novel?
No.
It won the National Book Award. And it is a story about essentially a young boy who is an amateur radio operator in World War II. And he sort of explores some of these themes around what we know and what we don't know, particularly about radio and sort of how that develops. Anyway, if you have time in your month off, Anthony Doerr is the author. It is wonderful. I would lend you a copy. All the Light We Cannot See. It's great.
Okay. Actually, if you just email me the.
I will. I would be happy to. I had the incredible pleasure, which I have never had, of interviewing him. Right. Nice. I think right about this time last year. Yeah, it was amazing. So anyway, you're talking about radio. So tell me more about why it is that radio you think sort of suffered from this human hubris thing.
Well, first of all, I'm not saying that it's hubris because I really don't know, but I will say that the atmosphere is plenty transparent to radio at a lot of wavelengths, at least. Radio covers a multitude of wavelengths, but we can observe cosmic sources of radio waves from the ground. And the technology to build radio receivers was around, at least since Marconi, so like the 20s or 30s, say. And I don't think radio astronomy really got going for at least 20 or 30 years after that. And I'm not sure why. It may simply be that nobody really had any reason to think there was anything out there producing radio waves. Or it may just have been the hubris of that Tyson says, well, if we can't see it with our eyes, then it's just not as important a kind of radiation. But I'm not sure. I'm not as quick to judge maybe as
right. I was going to say, like, what if hubris? I mean, I guess I want to sort of trouble what Tyson says here as well, because I'm not sure that I would call that hubris. Like, what if that's just about
short-sightedness?
Yeah, I guess I was going to call it a blind spot, which I know has some sort of ableist connotations to it. But I think there's also something to be said for the idea that, I mean, as a qualitative researcher, I spend a lot of time thinking about the idea that we can never fully control for things, and that, we can't, as much as we try to leave our bias to the side, we can't do that. But what if, to some extent, really what we're talking about there is about the limits of human perception, which is a biological function. Yes. That the idea that we can only perceive so much does serve us to some extent. I mean, we're not perfect, but
sure, I don't know. You could be overwhelmed by too much.
Exactly.
Easily.
And we are on the regular, right?
Yes, and some people more than others.
Yes.
And I'll say, for me, it's getting worse. I find it much harder to work in a noisy environment than I did 20 years ago.
That's so interesting. Really? It's harder for you now?
Yeah, I just find it harder to get so deep into that zone that the world goes away. And I used to be able to do it more easily. And, maybe I don't know what to blame it on. Maybe it's just because I've had more control over my own environment. Once you get your own office then you can close the door. Maybe that's when you lose.
It's just hard to go back, right?
To work in a noisy, chaotic background.
It's a really great point, though. I mean, to some extent, I mean, when I was an undergraduate student, it was relatively common for folks to have like computers in their dorm rooms and such, but I did not. And so I learned to write, scholarly write in a computer lab where there was a din of noise, or a coffee shop, a din of noise all around me. And I don't know if I don't know, I wrote my dissertation in coffee shops. I think I'm pretty good with the din of noise, but I think that you have a good point, that there is something again, to be said about what the limits of our attention are, and the idea that we are bad at perceiving the limits of our attention.
Yes, I certainly agree with that.
Don't say bad, but imperfect, because
Thank you, Mariana.
Sorry
I
about
so
that,
appreciate
Krista.
you.
Trying
Thank
not
you
to have
very
valiant
much.
judgments here.
Thank you. You are absolutely right. We we are imperfect at perceiving our ability to manage our attention. I think that is a really good addition there. So welcome back, everyone. Andy and I had, as usual, a great conversation on the live stream, as I'm sure all of you did have in your breakout rooms. I'm going to unpin us here, as I did with our last kind of portion of the conversation, and ask you if you are interested to switch to gallery view so you can see everyone's faces in the top right corner, and respond to this question as a group. So the question that we asked here, and Andy and I spent some time talking about hubris, or maybe what were some of the other things that might cause us to sort of slow our discovery as humans. So this is again from page 151 of my edition, at least, of this book. Tyson talks about how slowly the telescope developed, particularly to see bands of light invisible to the human eye, and blames human hubris for the lack of speed. What other scientific discoveries may have been hindered by hubris, and why do you think this is the case? So I would love to, again, hear from a couple of folks from the groups. What did you learn? What other scientific discoveries did you think about? Andy thought about radio, which I'm excited to talk about, but I would love to hear from all of you first. And again, you're welcome, just turn on your mic or raise your hand IRL in real life, or raise your virtual hand, whatever feels comfortable to you.
I'll go, Krista.
Thanks, Jen.
So we kind of were talking about hubris, but then we also mentioned some other things that are just human that also have derailed some scientific advances. And so one of the big things I can think of is people always want to know, where's the money, right? Especially nowadays when there's a lot of grants and, you've got to find donors and all that. Way back when you were privately rich, you could ask whatever questions you want, but it's very hard for scientists to do science just because they're curious about a question. And there are so many discoveries that have been made just because people were curious that in the long run turned out to be amazing. Right. And so one of the examples I kind of brought up that I'm assuming would have happened is I am guessing that if Kennedy didn't want to beat the Russians in space, we wouldn't have had a space program. Right. Like everyone's like, well, why go to space? That's a lot of money. That's a lot of risk. Are we mining things, which is now a big talk? What are we getting out of this? And I also said I had read, this was a while back, but a scientist who was doing work on mantis shrimp, which if people don't know mantis shrimp, they can basically break the sound barrier with how fast they punch. And she had a government official come up and was like, well, why is this useful? And so she had to come be like, oh, well, we can use it for crash helmets and yada, yada. And she had another scientist from a third world country come up and say, you don't know how lucky you are that you can do science just because you want to do science, that you have this question. She's like, a lot of us are so, kind of pigeonholed into, you have to do a science where there's going to be money at the other end. Right. And I think that unfortunately, there's a lot of stuff that we have out there that we just want to see this at the end when we fail to see the big picture, like with this light microscope, right? We're like, well, what's the point? It's this big expensive thing. What are you even going to find about it? Well, let's build it and see. That's kind of what science is.
Thanks, Jen. Yeah, I'm so glad that your group sort of dug into that conversation around the idea that a lot of times I hear folks talk about the problems associated, I don't know if that's the right word, but associated with science for science's sake, right? The idea that you might do research just to answer a question that maybe is an unknown for us as humans. But I think that one of the points your group is trying to make is the idea that even though those questions may not seem immediately applicable, I think science has afforded us lots of opportunities to see places where immediate applicability is not necessarily a good litmus test for good science. And I'll share with some of you an example from one of my colleagues who for many years studied communication around pain. between patients and providers. And she struggled to get funding early in her career in the early 2000s because there just wasn't a lot of research dollars. There wasn't a lot of interest around how patients and providers communicate with one another about pain. And then the opioid crisis happened. And all of a sudden, my colleague has more funding than she knows what to do with to teach and train physicians to talk about pain, to teach students, medical students to talk about pain, to teach patients how to talk about their pain appropriately to their providers. There's lots of those moments where we think we might not need this until we do. And I think that that's an interesting part of the science process here. So Andy, you and I talked a lot about the idea that when we think about how discovery is made, that it might not necessarily be about hubris, but that it might be about other sort of factors that would shape the scientific discovery process. Can you talk about what some of those other factors are, particularly as it relates to your example of radio?
Sure. I mean, sometimes I think it's just a lack of imagination. And so with radio, just to give people a little background, I was talking about the fact that there are probably good reasons that Tyson didn't bring up for why we didn't really start doing infrared astronomy or ultraviolet astronomy or X-ray astronomy for as long as we did. We knew those things existed, but there were reasons not to do it. Radio astronomy, I think, is the one area where we really could have done that at least decades earlier. But radio, I want to tell a related story, which is about the discovery of radio waves. The first known instance of a human being creating a radio wave on purpose was Heinrich Hertz, the guy that we have named the unit of frequency after. And Hertz did it in the context of a lecture demonstration in a graduate class, which a lot of people wouldn't do anyway. He was teaching a graduate class on electromagnetism, and he set up this thing that sent a radio wave about 2 meters across the front of the room. And basically all he could do is make a spark on one side, and then it would go click on the other side. With big antennas. And his students asked him what that might be useful for. And he said, it's not useful for anything. It's just to prove that Maestro Maxwell was correct. And this was a brilliant guy. I mean, he was a brilliant physicist. And he had the wit to be the first person to build a thing that could purposefully create a radio wave. And yet he didn't have the imagination to think, oh, this will be useful someday. But he wrote it up. And Marconi, who was a teenager reading physics journals while on vacation with his family, read about it. And he was the one that thought, oh, that's great. I'm sure I can find a way to make use of that. And
Andy, you have an upcoming vacation, right? I mean, no pressure, but you know.
That's right. I told Krista earlier, I'm going to be on a road trip. I can get my wife to drive and I'll read journals in the passenger seat. I don't think that's going to fly. But it's a wonderful story. I mean, the fact is, Hertz just didn't, he had a great imagination for some things, but he didn't have the imagination to ask what this would be useful for. But there are other things, you know, sometimes it's scientific orthodoxy. And, you know, this isn't something that a lot of scientists like to talk about. But the fact is, at any given time, in any given science, there are widely accepted ideas. And those are really hard to get rid of. Eventually, it usually happens. I suppose it's possible that there's an example currently now where the orthodoxy hasn't been overturned yet, but I don't know what it is. But I can think of some historical ones. For instance, the idea that disease was caused by microorganisms, the so-called germ theory of disease. That was not a popular notion when it first came out, and the biggest pushback wasn't from people who just didn't believe that something so small could hurt you. It was from people who already had a theory, which was the miasma theory, that there were vapors, bad smells that came in through your windows at night. And you know, the way to avoid disease was to live in stuffy rooms with no ventilation, which we all know right now is probably the worst thing to do if you're trying to avoid the COVID virus, is to get into stuffy rooms with other people instead of being outdoors. You know, and the Einstein's ideas about relativity had a very tough time making headway, as did quantum mechanics. And there are hosts of examples like this throughout the history of science, where it's an orthodoxy that's the problem.
Yeah, I think that's a really good point. I think that I was going to use the term inertia, but it felt really punny in this space. But there is, to some extent, that just the movement of a field in a particular direction that I would think makes it really hard for folks that have unorthodox ideas to sort of get the space they need to have those conversations. So I want to make sure, I'm looking at the clock here, and I want to make sure that we talk a little bit about dark energy, in part because we had a participant question, and because it was my favorite chapter of the book, which was chapter 6, which is about the discovery of dark energy, which I loved this chapter very much. So one of the things I liked, and again, communication scholar, so take it with a grain of salt, was really about the conflict between, or Tyson creates the conflict. I know no conflict is truly as cut and dry as he claims it to be, between we're talking about dark energy, between the theorists and the observers. Can you talk a little bit about dark energy, how dark energy developed in the field as a theory, and how that discovery sort of changed your field, just so that we can have a better understanding, I think, beyond what Tyson talks about?
Yeah, sure. So this is, in some ways, it's one of those very difficult questions, because it really is something that's built into the mathematics. Basically, what this all comes down to is whether the universe is expanding at a constant rate, if it's expanding more slowly than it did in the past, or if it's expanding more quickly than it did in the past. When Einstein developed general relativity, he built in a term that was basically, oh boy, this is hard. I've got to just give a tiny little background. I'm going to go back to this building a mathematical model thing. So when you build a mathematical model, you're creating functions or mathematical procedures that describe the world. And sometimes you need some flexibility because you don't know everything that can happen in the world yet. So you build in some extra terms. You say, all right, this term may be there, or it may not. Maybe it's zero. And as a physicist, often you just say, all right, this term, we're going to multiply by some variable that we'll call little a or little d or whatever, you stick a letter on it. And maybe that's zero. And if that's zero, then this term won't make any difference. But I don't know that it's zero yet. So I'm going to withhold judgment and just put it in there and leave it to a later date for somebody to measure that. Well, Einstein built in this term called the cosmological constant because he knew that the other parts of his equations predicted that gravity would cause the universe to contract. And he wanted there to be a term there in case the universe wasn't contracting to say, all right, well, this will keep it expanding. Don't know where it comes from, but it's a mathematical term that describes keeping the universe pushing back on gravity. Yeah, someone in the chat just said it's a fudge factor, and yeah, it's kind of a fudge factor. I'll go with that. Now, Einstein then found that that wasn't necessary. He said, well, it turns out the universe is expanding. So this term, isn't necessary. There's just enough inertia there, and gravity's not pulling back hard. There's not so much mass that gravity is going to cause the universe to contract. But then later, it turned out that there wasn't that much mass, and the mass didn't match up. So he said, all right, that term was a blunder. That's the biggest blunder of my career, he called it. But then more data came in and he needed it back. So, there's this back and forth with Einstein with the cosmological constant. Then, Einstein passes away in the 50s. And more information comes in about how the universe is expanding and how old it appears to be, and how much mass we can account for by observing all the stuff out there. And the picture just becomes muddier and muddier. And so now we have two things out there, dark matter and dark energy. Dark matter is other stuff like regular matter that adds to the gravity part. And we know it's out there. There's definitely more stuff that things we can see are attracted to gravitationally than we can account for. Right? So there's something we can't see, but we know that other things are attracted to it by its gravity. But then there's this other thing that says the universe is expanding faster and faster, way faster than would be allowed by all that gravity. So there's also something that's pushing it apart. That's the dark energy part. So dark energy is just, it's another name for that fudge factor that causes the universe to expand. And there's all kinds of hypotheses about what these things could be. And to answer Michael's original question, I don't really have a favorite. I think the ideas about dark matter are a little better developed, but as in the sense that there's more sort of candidate things, whereas dark energy, it's still like, yeah, it's this field, it's pushing. That's what we know about it. It's our name for the thing that is causing the universe to expand more and more rapidly. I do want to put a plug in here, and I'm just going to grab, if you don't mind, Krista, I'm going to put a link in the chat having to do with dark matter. Because I found there's just a really nice article in Symmetry magazine, which is an online publication that, for people who are interested in physics in general, is a really good choice for people that want sort of a lay level explanation of physics topics that's done by physicists and vetted carefully by physicists and is as little wrong as it can be. So I just threw that link in there. It's an article in particular about dark matter, but Symmetry magazine is a great publication as well.
That's wonderful, Andy. Thank you so much for that. I know that folks will appreciate that. That's one of the things we love about this little club here, is that folks tend to share resources and ideas and suggestions for things that we can read beyond the topic of the book for this month. And I appreciate your conversation here as well, because I think it does help push us to think about, beyond, again, we talked about the idea of science for science's sake, and this, the idea of, particularly with the concept of dark energy, not fully there are things we still just don't understand. And I think for me, that's one of the things that I liked very much about this chapter, sort of Tyson's ability to talk about, here are the things that we are pretty confident about and the things that we know. And here are the things that just Andy, you articulated it well. Yeah, that we've got to develop some kind of structure to be able to talk about it if we are going to hypothesize in that way. And I think for me, that's really important, right? The idea that we have to have some language to be able to push the scientific thinking forward. I'm looking at the clock here. Oh, go ahead, Andy.
I was just going to say, I realized I didn't answer your question about theory and experiment.
That's okay.
Theory and observation. I can go there if you want. But
Nah, I think rather than that, I've got a final question. I'm going to put it in the chat just because for me, I think it is one of the things that draws together the science and the humanities, which is one of the things I always like to do, particularly with our last question of the night. Rather than send everyone to breakout rooms again because of the time, I want to just noodle on this question a little bit, give you all maybe potentially a chance to respond. And then also to give you all a chance to ask Dr. Gabrin some questions. So the last chapter of the book encourages us to see the relationship between ourselves and the universe. I saw an interview, as I mentioned in preparation for today, with Neil deGrasse Tyson, where he said the following, and if this is in the book and I missed it, I'm sorry, but he said it in the interview. The cosmic perspective on the world, which is really what that last chapter is about, can make you feel small and insignificant, or it can be liberating and uplifting. And my question for you is, which is it for you and why? And I will share that for me, I actually, like, again, maybe this is something I should have disclosed at the beginning of this conversation, that I've never taken a physics class. I just never had the occasion to do so. And so I loved this book in part because it did feel really liberating and uplifting to me to think about these concepts within the context of just how little we know and just how powerful the human process of reason is. It just felt really beautiful to me. And so I would love to hear from all of you. Did you leave this book and feel like, I feel like I'm just this little cog in the machine. I don't know what's happening in the world, which I think sometimes, I will share, I think that Tyson, like in his sort of tongue-in-cheek approach to talking about things, can make you feel kind of small in the universe. But for me, it felt really, really uplifting. Oh, look at that. It feels good to know that we don't know everything. I love that. Yes, thank you. We want to hire that kid for the next Books, Booze, Brains. Okay, well, just books and brains, no booze for that kid. All right, so thoughts from the group. Which of these did you feel insignificant and small, or liberated and uplifted? I'd love to hear from some folks in the room. Michael says liberated. If you want to add any context, Michael, you're welcome.
Yeah, I like the idea of the scale of the universe and how small we are. And it's kind of frightening, but it also like it allows you to really minimize, I think, the pettiness and kind of maybe ego or narcissism that drives so much of our history and behavior. And when you look at it in terms of how small that is, like it helps you focus on the bigger things, like, the science and the wonder that's kind of implied by the scale of these things. It's so amazing. I mean, you could spend lifetimes just studying science and you'd still be amazed. I feel like that's how I feel like it's uplifting to me,
I agree with you, Michael. One of the things, some of you know this, that a few years ago, 2 years ago, I guess right before the pandemic, I led a series of conversations between scientists and people of faith, who, as we know, are sometimes the same people, and to talk about the idea that there's sort of a Venn diagram of ideas about a sense of wonder about the world, about the sense of asking questions about what we know and what we don't know, about being able to sort of trust one another, and how that shapes our perspective on the world. So glad to hear you say that, Michael. I see that Jessica raised her hand. So Jess, go ahead.
I would say that I didn't really feel either. Whenever I, think about space or somebody's talking to me about space, it's not that I feel small and insignificant or liberated. It's like I'm in awe how connected we are to the universe, and like the same mechanisms that you can see on our planet, and even within our own bodies, those same things that kind of propel within the rest of space. And it's just because of course they do. Why wouldn't they? So I always feel like insanely connected. Like how can
Jess, it looks like you want to unmute there. I'm not sure what happened. Sorry, I missed the last part.
I was done.
Thank you. No, I agree with you. That sense of connectedness, I think, is really powerful. And I think one of the things that I liked very much about this book is I think Tyson does a good job of talking about how things are all connected. Mary Teresa, I think that you were next. Go ahead.
I pretty much believe what you just said, Jessica. I felt connected. I also felt enlightened, if I may use that word, and a calming effect. It didn't frighten me that there's not an answer all the way to the end. You know, well, where did it all come from? It just was so wonderful, and it's a bad word, but so amazing to hear how things move around, how this works and that works. It's like a giant continuum to me. So I felt elevated.
Well, Mary Teresa, I'm glad to hear you say that. I actually like the word wonderful to describe this because it is about feeling full of wonder, right? That sense of feeling full of you know, the idea that we can discover things and that there are still plenty of things to discover, which for me is really exciting. Andy, I want to give you the last word here. And also, if folks have questions for Andy in the chat, go ahead and throw them in there. But Andy, thoughts about feeling small and insignificant or feeling that sense of wonder? What are your thoughts?
Yeah, I definitely, I find it very uplifting. To me, it's just the way I've always felt about things. I mean, if I see a mountain, I suppose I could feel like, oh, that mountain is so big, I can't, you know, I'm insignificant compared to it. But I would much rather say, all right, that's an opportunity. I'm going to try and climb that and see what the view is like. And to me, that's what science is all about. It's about climbing that mountain. There may be some difficulties along the way, but once you get even a little way up, the view starts to be wonderful. And the higher up you go, the bigger and better the view gets.
I'm going to give you credit for that metaphor, Andy. That's a beautiful metaphor, I think, and a really good way to end the conversation tonight. If everyone would please join me in thanking Dr. Andy Gavran for serving as our guest expert for this evening. Andy, this was a wonderful conversation, so much fun. And I don't know about all of you, but I went into this book not knowing what to expect, and I really had a ton of fun reading it this month. So thank you all. And again, from the bottom of my heart, all of you are just an incredible community. Thank you so very much for sticking with us during the pandemic, during Books, Booze, and Brains. I am sorry that I won't be serving as a facilitator anymore, but I know that we're going to find somebody great to replace me. And I'm so looking forward to the opportunity to participate as a member of the group. So thank you, Andy. And thanks again to my amazing planning committee colleagues for the great opportunity to work on this project, to work with all of you. Have a great evening, everyone. Be safe, and we will see you again, not in June, but in July. Take care, everybody.
Well, thank you for the invitation, and thanks to everybody for coming. You know, getting on Zoom, many of us have had plenty of Zoom, and to ask people to get on to Zoom again after dinner, that's a bit much. So thank you for giving me your attention in this difficult format.
It was great to see everybody. Take care.
Thank you.
Bye-bye.